It is given here. So this portion marked by the red line, it is nothing but a DC motor. So suppose you have a separately excited DC motor. Like this, and you are putting a terminal voltage here. This is your VD. Since we are putting a terminal voltage VD across a DC motor, and there will be a back EMF in the DC motor as well. So this should be my back EMF ED. So what should be the equivalent circuit of this DC motor? The equivalent circuit of this DC motor, it should be, there should be a DC source which will represent a back EMF ED, and then the circuit should have a resistance, that is the armature resistance, and then we will consider a inductance, that is my armature inductance, and then it should be applied to a input voltage, that is my VD. Now you might ask me, sir, this is the DC source, so why we are considering the inductance here? Because for DC, the inductance becomes, inductive reactance becomes 0, right? So one thing to remember here, if your input voltage is pure DC, meaning there is no ripples in it, meaning there is only the fundamental zero frequency component present in the input voltage, right? But most of the cases, when you are rectifying something, your output voltage, is it purely DC or it's a pulsating DC? Pulsating DC, right? So if you take the Fourier analysis of that one, you will find that with zero frequency component, there are other frequency components are also present in the input waveform, right? So the inductance here, or the inductive reactance here, it is nothing but twice by L multiplied by F, right? So since it is not purely DC, so this inductance will act like a zero impedance for the fundamental zero frequency component, right? But it will offer some impedance for the other components, right? So that's why we are including a inductance here, because this input is not purely DC, rather it is a pulsating DC. Make sense?
Sir, can you explain again?
Yeah, sure. As I said, if it is purely DC, meaning if you do the Fourier analysis, you will find only the zero frequency component is there. And if there is a zero frequency component, what will happen here? If you put F equals to 0, means the inductance, it will become short circuited, right? But if it is a pulsating DC one, so although it is DC, but it is not purely DC. Meaning if you do the Fourier analysis, you will find that instead of having a zero frequency component, it will have some higher frequency components as well. So this impedance, it will become 0 for the zero frequency components only, right? But it will offer some impedance for the high frequency components, right? So that's why we cannot ignore the inductance in the circuit, because we are providing a pulsating DC. If it were the pure DC waveform, then we will represent the DC circuit with a simple resistive load rather than having a RL load.
So, sir, the ED is not constant either.
Sorry?
So that means ED is not constant either.
No, we are considering ED, but this ED is also not the pure DC form. It is the pulsating one as well. Right? So both are pulsating. So now, in the previous class, we were discussing about a thyristor circuit, and we said that we are delaying that firing angle alpha. So here, after this period, we are providing a pulses for T1 and T2. So suppose this is my T1, this is T2, this is T3, and this is T4. So before this thing happening, again after a certain period alpha, we are providing a pulses for T3 and T4. So you can imagine that from this point to this point, which are the thyristor that is operating, T1 and T2, right? And after this period, when you are applying a gate pulses to T3 and T4, T3 and T4 it will start operating during that portion, right? And before T1 and T2, during this slight portion here, which are the thyristor that will be operating again, T3 and T4, right? We discussed that in the previous classes, last two classes, right? And whenever your T3 and T4 is operating, meaning T3 and T4 is operating, your input voltage is positive. Input voltage positive means this is the polarities, right? So if this is the polarities, then your positive terminal it is connected to T4, so the positive terminal will appear here, and this positive terminal, the negative terminal it is connected to T3, so the negative terminal will appear here, right? So your output voltage here, suppose this is my VD, so your output voltage here would be the exact opposite of the input voltage which is shown here. Make sense? Now, as soon as you provide a gate pulse for T1 and T2, although T3 and T4 is operating, now you are providing gate pulse to T1 and T2. If there was no inductance in the circuit, then what will happen? The current immediately jumps to the peak value, right? What was being carried by T3 and T4. But since you have an inductance in the circuit, so the inductance doesn't allow the current to jump to its final value within zero time, right? It takes some time. So that time is denoted by this commutation time. So during this portion here, this portion will be lost due to commutation or due to presence of inductance in the circuit, right? And after that, what will happen? You have a back EMF here. So if you have a back EMF, when the current can flow in the circuit, suppose this is your ID, so when the current can flow in the circuit, when your input voltage is higher than the back EMF, right? So as your input voltage is higher than here, the back EMF, then what will happen to the current? It will start charging up to this point, right? Because your input voltage is higher than the back EMF, right? So now if the input voltage goes below the back EMF, then what will happen?
Discharge.
The voltage across the inductor it will be negative, right? And if the voltage across the inductor is negative, then what will happen? The inductor will start discharging, right? So after this point, the inductor will slowly discharging when it will start charging again when T3 and T4 starts conducting again, right? And then when the voltage, input voltage becomes zero, less than the back EMF, then it will start discharging again like this, right? Since we are considering a practical circuit, so that's why we are considering the current charging and discharging. But previous two class we discussed that the current is unidirectional, right? Meaning there is no ripple in the circuit, because we are considering the load to be a idealistic highly inductive load. But in practical cases, no matter how big inductance it is, you will find some ripple in the output circuit. The output will never be exact DC.
Sir, could you please draw the wavelet separately?
Which one?
The inductor one.
You do it by yourself.
My eyes are blind.
What is problem with that?
There are too many waveshapes.
Yeah, that is fine. Whenever you will be drawn in the exam, you will do this thing, right? I cannot tell you to draw everything separately. Okay, no problem. So suppose this is my sine wave, and we are putting a pulses at an alpha degree. So this is my alpha, and again from here we will be providing another alpha degree delay for the negative portion. So now what is happening here? So during that time we are providing a gate pulses for T1 and T2 here, and again here we are providing a gate pulses for T3 and T4. So just before you are putting a gate pulses, suppose this is my input, you are getting the output voltage here. So during that portion, when for this portion from here to here, T3 and T4 is operating. So if the T3 and T4 is operating, what will happen to the output voltage? Although your input is positive, then your output will be exact the negative portion of the input voltage, right? Now, in the previous case, when we didn't consider the commutation, and for the commutation, since you have a inductance in the circuit, then there will be some time for which the 4 of the thyristor will be conducting, right? So this time we are considering it as a commutation time. So suppose this is my commutation time. This portion, this is my commutation time. So for this portion, your output voltage it would be 0. Why it is 0? Because 4 diodes are conducting, meaning these two terminals becomes short circuited, right? Make sense? And then your T1 and T2 starts operating. So if your T1 and T2 starts operating, then what will happen? Now this positive terminal, since T1 is operating, so it will come at the top, right? And for the negative terminal, since T2 is operating, so it will go at the bottom. So in that case, your output waveform will be same as the input. But here is one condition, is that there is a back EMF present here, right? So if there is a back EMF present here, so if I consider this to be my back EMF, so suppose this is my back EMF, EB. So what will happen then? So from here, although your output voltage would be same as the input voltage here, like this, but still we have some back EMF present in the circuit, right? So if your input voltage is higher than the output back EMF, then what will happen to the inductor current? The voltage across the inductor it will be positive, right? So if the voltage across the inductor is positive, then what will happen to the inductor current? So from this point, up to this point, the inductor will be charging, right? And after that, during this point, the inductor will be discharging, right? And again, this output would be negative here because T1 and T2 is still conducting, but here we are providing pulses to T3 and T4, and as soon as T3 and T4 starts operating, so there will be a commutation time again, and after that you will find that your output voltage will be exact replica of the input voltage like this, right? So here your input current will be reduced to this point, and after that, since your input voltage is again higher than the back EMF, then what will happen? It will again start charging, right? And then it will be discharging like this. Clear now? And during that portion also, the current will be discharging here because here you will find that your output voltage is negative, right?
Sir, what will happen to the inductor current in the commutation time?
Commutation time. During commutation time, what is the voltage across the inductor? Negative. What is the current here? I is what? The average value of the inductor we have discussed so time in steady state the average value of the inductor is 0, right? Average voltage for the inductor is 0. So what would be your current? The average value of the current, it should be simply your Vd minus Ed divided by Rd. So that is the average current. Okay? And if there is no input voltage, meaning this source will try to flow the current in the opposite direction, right? Meaning it will force the inductor to discharge. Make sense? Okay, so now tell me, here if we consider this point, this is my ID max point. This is my ID max point, and this minimum point is my ID mean point. So tell me, what is the total area that will be lost here? The total area lost here is what? This angle is your commutation angle U, right? So it should be 0 to U Vm sin omega t multiplied by d of omega t, and it should be equals to omega Lt multiplied by current is during this commutation period. What is the current? Is it IL max or IL min? IL min, right? So it will be transitioning from minus ID min to plus ID min, right? Dn. And if you do that integration, you will find that this value equals to omega Lt multiplied by twice ID min. One thing, why we are considering its LT? Because now we are not considering only the source inductance, rather we are considering the source inductance and the armature inductance. So what we mean for LT is that the total inductance, that is the combination of both source inductance and the armature inductance. Okay, so what would be the output voltage then? What was my output voltage if we don't consider the commutation time? It was twice Vm over pi multiplied by cos alpha, right? And this commutation time is happening twice within the one period, right? So it should be minus 2 multiplied by area divided by 2 pi, right? So if we cancel out this 2 by 2, it should be area divided by pi. So what is the area? This thing, right? So what would be the average value then? Twice Vm over pi cos alpha minus what is W Lt to ID mean over. We have derived this equation several times in the previous last 2 or 3 classes, right? Any question regarding this?
স্যার এখানে স্যার মাইনাস আইডি মিন থেকে আইডি মিন নেওয়ার কি দরকার ছিল? এখানে তো স্যার মাইনাস নয়, মানে ওয়াই এক্সিসের এখানে তো আইডি মিনটা তো মাইনাসে নেই, মানে পজিটিভ, বাট আইডি মিন।
We have said several times that whenever we are talking about this thing, we are talking about the input current here. So input current direction, it is changing, right? Whenever T3 and T4 is operating, the current is going in one direction. When T1 and T2 is operating, it is going in the other direction.
Okay.
So that's why we have to check the total current change, and the current change will be twice of the individual magnitude. So now that was the analysis when we are considering a continuous current, meaning the current never drops to 0, or we are considering the inductor current high enough to maintain a continuous current level. What happens if your current is not that much and current drops to 0 after a certain period of time? What will happen to the output? So now here we are considering a discontinuous mode. So in that discontinuous mode, what will happen here again? This is my 0 point. So up to this point, we are dealing the angle by certain angle alpha, and then here we have some commutation time, that is my u, and before that my T3 and T4 is operating, and here we are providing a pulse, get pulse for T1 and T2. So from here up to this point here, T1 and T2 will be operating, and after that there will be you will put a get pulse here again for T3 and T4. So from this point up to the remaining part, your T3 and T4 will be operating. So I think you have understood the waveform, right? Because we have discussed it over several times, I think, that waveform of that, right? Voltage waveform. So since T3 and T4 is operating, suppose this is my T1, T2, T3 and T4. So during this negative portion, since T3 and T4 is operating, so your output would be negative. Okay, so one thing I forgot to mention here is that, as you can see, your output voltage is slightly lower than your input voltage. Here, as you can see, your output voltage is slightly lower than your input voltage. Why is that?
Because of back EMF. Back EMF.
No, this is because we are considering a practical thyristor, right? So whenever the practical thyristor is operating, it will have some power loss or voltage drop, right? So that's why your output voltage will be slightly lower than the input voltage, because of we are considering a practical thyristor there that will have some drop in it. What is the practical drop of the thyristor? 1 volt or 2 volt, something like that. Yeah, when it starts conducting, meaning it will act like a switch, right? But still the switch has some resistance in it, right? So for that one there will be some voltage drop across it, right? Okay, so now here, as you can see, the current, it starts discharging, and between these 2 points the current becomes 0. So if the current becomes 0 during that period, so meaning the current is 0 here. If the current is 0 here, what does it mean? Your T1, T3, T4, T2 all are on or off?
I mean, they are conducting.
On or off? There is no current. All are off, right? So meaning your input is disconnected from your load, right? So in that case, what will be the output? Output should be ED, right? Because there is only one source here. So if there is no drop between LD and RT, so this voltage source, it should appear across the terminal, right? So the only difference here is that when you have a continuous current, you will find this area lost due to commutation, right? But since there is no current here, so the voltage jumps to the back EMF because no current is flowing inside the load. So in that case, similarly, you will find here this portion, it was lost due to the continuous conduction of the current, right, during commutation. But since here there is no commutation because current already goes to 0, so there is no transition period, right? So what will happen to the output? Since there is no current here, so there will be no drop across the element. So entire back EMF it will appear across the output. So that's why you will find your output appears like this. And after that, what is happening here? During this portion, since your input is higher than the back EMF, then what is happening? The current starts charging, right? And after that current drops down to 0 and remains 0 for a certain period of time. So now tell me, what is the lost area in this case? Previously, whatever area is under commutation, we consider it to be the lost portion, right? But here, what is the lost portion?
80.
What is the lost portion? This point here, this area, it is the lost portion, right? This area here, it is lost, right? Right? So tell me, which average voltage will be higher? Continuous mode or the discontinuous mode? Why is that? Because we are having a lost portion that is less than the continuous mode, right? Make sense? What is the lost portion here? If there is no current, means there is no commutation, right? Why this thing becomes 0? Because during commutation, the 4 diodes look to operate together, right? Because the current is transitioning from 2 diodes, 2 thyristor to another 2 thyristor, right? So in that case, 4 thyristor will be short circuited, meaning the output here it would be 0. But in this case, since the current is discontinuous, then what will happen? This 4 thyristor, it will become off, right? And if it is off, there will be no current in the circuit, meaning there will be no drop across the element. So entire back EMF will appear across the output. So we will find there is a back EMF portion here until unless the circuit starts operating for T1 and T2, where the voltage becomes higher than the back EMF and the current starts flowing again. Any confusion so far? Anyone? Anyone? Everybody is busy with this mobile phone. Okay, so that's what is shown with this figure. So here, as you can see, if your current is low, then it will be operating in the discontinuous mode. So whenever it is operating in the discontinuous mode, what is happening here? Your input, the output average voltage, it is higher. As long as your current becomes high, then it probably it will be operating in the continuous mode. And if it is operating in the continuous mode, what will happen to the output voltage? It will be lesser. And one thing is that you know your output voltage is what? Twice Bm over pi multiplied by cos alpha, and then you have subtracted some portion with it, right? So if you increase alpha, then what will happen to the output voltage? It will drop, right? So as you increase the value of alpha, as you can see, your output voltage it becomes lesser, right? Make sense? So during that portion, since the current is lower, here we can think that it is operating in discontinuous mode. And after a certain value, although we don't know which is the what is the barrier magnitude for the discontinuous or the continuous one, but we'll know for sure that if the current is higher, there is a high probability that the current will be continuous. If the current is lower, there is a high probability that the current will go to 0 quickly. So if it is operating in discontinuous mode, what will happen to the output voltage? It will be higher. If it is operating in the continuous mode, the output voltage it will be lower. But what is the expected one? Continuous or the discontinuous one? Why is that? Why is that? Because it is driving a DC motor, right? If your current becomes 0, then what will happen? If your current is 0, torque is what? IL cos B, right? So if your current becomes 0, what will happen to the torque? Torque is also 0, right? So the torque will be fluctuating from 0 to a certain value. So the average torque in the DC motor, it will reduce. Make sense? Or it will be fluctuating torque. But what is our expectation? It should run smoothly at a constant speed, right? So the more the output current will be ripple free, that is the expectation we have. But in a practical case, although how much higher inductance you put, the current never becomes a DC. It will have certain ripple in the output current. Any question? So whatever we have discussed here, it is from Nidmohan's book, page number 133 to 136. Okay, now previously in the last class we discussed about the two quadrant. We said when my VDC is positive, IDC is positive, it is operating in the first quadrant, right? Or it is operating in the conversion mode. And when your VDC becomes negative, it is operating in the fourth quadrant, meaning it is operating in inversion mode, right? Right? So now, if this is my 0 position and we are dealing alpha by certain angle alpha, and suppose this alpha is 120 degree. So what was the condition here? When it will be operating in the conversion mode when my alpha is less than 90 degree, right? And when it will be operating in the inversion mode when your alpha is greater than 90 degree. So here we are considering your alpha is around 120 degree. So what will happen? So before this alpha, which are the thyristors that will be operating? T3 and T4, right? And here we put a gate pulse for T1 and T2. So from this point up to this point, which two are operating? T1 and T2, and here we will put another gate pulse for T3 and T4. So from this point up to the remaining point, T3 and T4 will be operating, right? So now whenever T3 and T4 is operating during this positive portion, you will find your output voltage is exactly the opposite replica of the input, because we have discussed it several times in the class. I will not go into that detail again. And after that, since this is T1, this is T2, this is T3, this is T4, and during one commutation, these four thyristors will be operating together, because it requires some time for the current to transit from one pair of thyristor to another pair of thyristor. We will find there is a commutation time, right? When four of the thyristor will be on and your output voltage becomes 0, because we are considering the current to be continuous here. If it was not continuous, then what will happen to the output voltage? It will become ET, right? So now from this point, let me draw it with another color. So from here, after that commutation, what will happen? This T1 and T2 is operating. So if T1 and T2 is operating, meaning T3 and T4 is off. So now what will happen to the output voltage? It will be same as the input, right? So here you can see there will be a very small positive portion in it, right? And if the polarities of the input is changing, then output will be changing as well, because still T1 and T2 is operating here, right? So you will find this portion it is negative until unless T3 and T4 takes charges again here. So now here you can see there is a very small tiny positive portion and the remaining portion are negative, right? So what should be the average value?
Negative.
What should be the average value?
Negative.
Negative, right? So that's why whenever your angle is greater than 90 degree, you will find your output voltage is negative. What is the maximum extreme point? If you switch that to 90 degree, then what will happen? You will have some area positive equal to, again it will be switched here. So your positive area will be equal to the negative area. So in that case your average voltage would be 0, right? And that is also evident from your equation, because your equation is what? 2 Vm over pi multiplied by cos alpha. When alpha is 90 degree, then since you have a positive portion that is equal to the negative portion, they will cancel out each other. So your output average voltage it will be 0. Okay, so last topic for the Ramadan Mubarak. So today we are going to end the thyristor class or the AC to DC converter class. From tomorrow we will start talking about the inverter class, meaning DC to AC, and hopefully in the next week we will discuss about AC to AC converter or slight flow converter, and then we will discuss about some practical application of these circuits. From starting to the end, I have covered very little portion of the syllabus. So I don't think that is too much for you to cover for the time. That's why you will be charged up. Your output voltage is like that back here, right? Okay. So do you remember when we discussed a three-phase circuit with the diode rectifier? What was the output? The output was the ripple like we see here. So do you remember this ripple? It was like this, right? The output ripple. This voltage was VAB, then it was VAC, then again it was VBC, then again this was VBA, then again this was VCA, and then it was VCB. So what is happening here? Why it is VAB is getting higher here, or we are getting only VAB across the output? So what is VAB? VAB means VAL minus VBL, right? So here as you can see, the VAL is this line, right? What is VBL? VBL is this line. So as you can see, up to this point, VBL was higher. After that, which one is higher? Sorry, I made a mistake. This is your VCL, right? So what is your VBN then? I just made some mistake here. Sorry for that. So suppose this is, I might need to redraw it with another color. Okay. So this is your VBN. Okay. So now whenever you are talking about VAB, so VAN minus VBN, so this is this area. That was higher. Then VCN, because VCN is your red color line, right? But after this portion, this crossing point, what is happening here is that your VBN is getting lesser, but your VCN is getting higher. So if you make the difference here, you will find that during this portion, this thing is higher. So for this portion, your VAC is better. For this portion, your VAB is higher. And whenever your VAB is higher, then from here you can see VAB is higher. So which of the thyristor will be operating? For A, T1 will be operating, and for B, T6 will be operating, right? Right? So during this portion, which are the thyristors should be operating? T1 and T6. When VAC is operating, AC means A point is the same, but C is now operating. So for C, which are the thyristors would be operating? For C, it is T2, right? So it should be T1 and T2, right? When you have VBC, VBC means B and C. So which of the thyristors should be operating? T3 and T2. T2 and T3, right? So here it should be T2 and T3. And then BBA. So BA. So B is positive, so T3 should be operating, right? So T3 should be operating, and then for A, which one should be operating? T4, right? Then for CA, so for C, which one should be operating? T5. And for A, T4, right? Right? And now for the last one, VCB. So CB, so again for positive case T5, and for B is negative, so T6. So T5, T6. Right? This is exactly what it should be when your alpha is 0 degree, meaning your thyristor is behaving just like a diode. Okay? So now what will happen if your thyristor is having a gate pulse at a certain angle alpha? So what is happening here? We are delaying the circuit alpha. We are delaying the circuit by alpha. Then what will happen? If it were a diode, then as soon as the VAB becomes higher, it should operate, right? And you should have the positive portion like this, right? But since it is delayed by some angle alpha, so T1 and T6, it will not operate until unless you provide a gate pass here, right? So what will happen here? Instead of operating from here, VAB will start operating from here to here until unless VAC takes over after a certain point alpha. So again from here, VAC will take place and it will continue until unless VBC takes place after a certain angle alpha. And again it will be delayed by certain angle alpha where VBA can take place, and then it will continue like this. So instead of having a ripple like this, if we are dealing a certain angle alpha, your output waveform will look like this. Any confusion? Why is that? Because VAB is delayed by alpha, similar to VAC is delayed by alpha. Each and every line to line voltage is being delayed by alpha. So until unless the one phase is taking charge, the other phase which was conducting, it will continue conducting, right? So this way, if you see that equation, we want to see how this waveform might change with your firing angle alpha. If it is alpha equals to 0, it means you will have exact the same ripple as the diode circuit. But if it is delayed by alpha, and this alpha is 30 degree, then what will happen? Instead of starting from this point, it will be delayed by certain angle alpha for each and every phases. If you increase the firing angle again, then the delay angle will be again, and your output will have ripple like this, more and more ripple. If it is 90 degree, then as you can see, it will behave like this, and as we said before, you will have a positive area that will be equal to your negative area. So in that case, your output voltage, since it is 2 VA over pi multiplied by cos 90, it becomes 0. If you further increase the firing angle, then what will happen?
Negative
This output, it becomes
2 by pi Vm into minus half.
negative. And if you increase further the negative magnitude of the output voltage, it will be higher, and if you put alpha equals to 180 degree, it means it will behave like a diode, but the polarities of the output voltage would be reversed. So by changing the firing angle, we can choose to operate in any region between these two quadrants, keeping the current in the same direction. Make sense? So today's class we conclude here. If you have any question, just go through the topic, and if you have any question, you ask me in the next class. I will try to discuss that again. Otherwise, we will start inverter circuit from the next class.